right, generative AI and sensors. Let me start this by going racing. Race cars particularly, have a lot of sensors in them. And we can do some pretty cool stuff using some generative AI techniques I'm going to talk about today from the sensors data that comes off of these things. We're working actively with the Andretti global group, particularly in IndyCar, with these cars that go at the Indy 500 upwards of 240 miles an hour in qualifying. So that's the kind of speed of the data from the sensors that we have to actually react to in real time, literally high speed. As well as the streams that come from those data. So a lot of data is being given off by these vehicles. So we'll talk about that, and we'll talk about, okay, how can some of the generative AI we're using use to create virtual sensors, soft sensors, from some of that same data, and the correlations are in there, using some pretty high-end statistics to give us insights into things that we can't physically measure with the sensors that we have, using the data from the sensors we can measure. Couple of forward-looking statements. Pharmaceutical commercial, I'm not going to speed read that for you, but we are a public company. Let's talk about the speed of data when you're going 240 miles an hour, where every millisecond counts. At the Indy 500 last year, between 20 and 21, I believe it was a tie after 8 miles at 230-something miles an hour average of down to 1/10,000th of a second. So those are the kind of thresholds we have to meet.
Get ready. Green, green, green.
The difference here from just a sponsorship in a lot of ways is the fact that we're actually, doing work.
They're really able to push us into areas that we wouldn't even be able to go down.
What Zapata is doing here is something that they're going to be able to help every industry.
Can you use a little overtake for lap here?
We're also having Andretti learning cutting-edge AI. And that kind of give and take is really special.
It's been a building process to build the tools up, prove the tools out.
Okay, pit this lap.
We were under like 1% difference between what we were predicting would happen with the car and what actually happened with the vehicle.
Need a good one, boys. Steering wheel straight, foot on straight.
The knowledge of data analysis that they're able to provide really raises our level.
White flag, car 27.
What I'm most excited about with our future with Zapata is perfecting this system so we win races.
Good job.
Hell yeah, boys. Good work, good work.
They'll guide you in where to go. Victory lane, obviously.
I was hoping there.
While we love to talk about auto racing, this set of capabilities around time series data prediction is central to applications across telco, finance, industry, logistics, defense, and more. Zapata's sensor intelligence platform enables machine learning and generative AI to run on live streaming data in a broad range of deployment scenarios.
So the company spun out of Harvard in 2017 from a quantum algorithms lab. We use these advanced mathematics to be able to take sensor data on our platform and be able to process that data to create models based on historical data, and then update those models live with live streaming data from the sensors from the vehicles in this case, but also in other applications that we refer to in banking. We have Sumitomo Mitsui Trust Bank as a partner that's using the same kind of streaming data to stream real-time market data into their platform to get insights. So we can use the insights from these from the sensor data that's coming in live streaming into these generative models that we use to do anomaly detection, predictive modeling, sensor fusion, and combinatorial optimization problems. And actually, we use a combination of all of these different methods in several of the applications that we build for Andretti and for the banks and for others. We've had some pretty known customers, and we're currently a defense contractor as well. You can imagine where sensor data might be useful in the defense space for these kinds of contested environments. Very similar to what we're doing with racing, where you don't always have great connectivity. Sometimes it's only a 10 hertz channel to get your sensor data in, and you have to real-time update everything because things change in practice in the field, and that's exactly what's happening in the racing situation. So we do have a perspective on the current state of AI. You hear generative AI thrown around a lot. You hear about LLMs and chatbots, these language models. But one of our big views, and when we started, was we weren't really that interested in language. As a co-inventor of the technology that went to Syria, maybe to my chagrin, we weren't doing anything in language. But that was intentional. We wanted to really do the boring mathematical stuff, because we think that that's where a lot of the industrial value is going to come out of this technology. So we use complex operational data to train our models. That's not necessarily language. Could include language, but doesn't have to. And most of the time, it's the numerical data that we're collecting from sensor data, visual data, sound data, other types of spatial data that we're getting, and market data in the case of the banks. We use a quantum-based generative AI. On the most advanced models that we have, we use tensor networks instead of neural networks. This is just a higher-end math that does linear algebra a lot faster and better, and basically gives you better generalizability and expressibility on your generative models than what you can do with neural networks. And we believe that the breakthrough, really, things are coming full circle. When we invented the technology that's behind Siri, this was a set of multiple models working together to get to a result. But they were small models. I guess we could call them today small language models. They would notice something in the input, and this thing would see something else in the input, and they would work together to solve a problem. And we really think that that's the way things are coming back to. It's not going to be the one model that rules them all. Ha ha ha. We're going to have something trained on the entire internet that does everything for everyone for everything. It's more going to be the way human organizations work. You don't want the CFO doing the engineering, and you don't want the engineer necessarily doing the CFO's job. We have specialization for a reason. And we believe that it's going to be specialized models, and we'll show it in a second, working together to get the right answers and to get insights for the human that has to ultimately make the decision in the loop a lot of the time. And we do have an opportunity to put this on the edge. If you have these smaller models working on the edge, they can be, for example, on every hop of a telecom network, or on every hop of a grid in power management, for example. And we can use these things to be much more predictive. We can actually generate scenarios and generate synthetic ideas, scenarios, wargaming, if you will. And this allows us to be much more predictive of the future. It's not just regurgitating what we've learned from the past. We're actually feeding forward into the future, and that's the power of generative systems. And we believe that this gives, we don't think that this necessarily means that we're going to get rid of all the humans. ChatGPT is not going to get rid of everyone's job, but we do think it will. If you can generate text, if you can generate pictures, you can also generate different designs for a bridge, different designs for semiconductors, different designs for strategies, for trading, or for racing a car. And this allows us to enable the human decision makers to do better jobs with the sensor data that they're getting from the field. One of the unique things about our platform is that we've designed it from the ground up to be able to train on historical models, but update these models with streamed data. And we call this our sensor intelligence platform. The problems and challenges with sensor data and data at the edge is that it's usually high volume. It's usually high velocity of incoming data. It's hard to attain sometimes because I have a 10 hertz channel to get my data. And it's not always available. So it's you have to deal with incomplete and missing data some of the time. Data quality is a problem, data cleansing on the edge, data pipeline integrations. And we've really brought all this together in a platform that allows us to train a model on 20 years of historical data from these cars, which is terabytes and terabytes of data, bring that model to the edge, and then stream the data and update the model as things are changing on the track, which we'll show. So here's our partner, Generative Global, with their race strategy partners. Here, we had to really build things from the bottom up to be able to do this. Data architecture, data lake configuration, which comes with our platform. And we're using this in a lot of different use cases. We'll show you yellow flag prediction, lap time prediction, tire degradation models, virtual sensors and infrared channels for slip angle, race strategy optimization, and then dynamic setup databases for the car parts and what the databases do, what parts combinations do what on the track. So here's the yellow flag prediction model here. Ensembles of models. I talked about multiple smaller models doing specific things. Here we have 5 concurrent models that are running in parallel on 2 A100s at the track on historical data, based on historical data, and they're used to predict when there's going to be an accident, basically, when there's going to be an on-track incident that would cause the car staff to slow down. And that's a time when you really need to think about whether you should pit your car before that happens or after that happens, because a lot of times they'll close the pit, which means you can't change your tires, which is a real problem for strategy. If you get behind that, you could lose the race. Alternatively, if you know that the thing might be a yellow flag a lap before, you can pit your car before everyone else. They close the pits, and you're on new tires while they're all waiting. So that's how you win a race. So here you go. You can see here we have 20 or so in green. These are the historically what's happened. And the yellow dots are 5 models predicting the percentage on the y-axis of when there might be an accident. One of the models is looking 1 lap ahead based on historical data and what's coming into the track. 1 2 laps ahead, 1 3 laps ahead, 1 4 laps ahead, 1 5 laps ahead. And that gives us an idea of what's happening. So you can see it going up a little bit as we go, bam. So here we go at lap 26, we have an increase to about 50% that there's going to be a yellow flag. We've got over a 50% chance. The models are saying there's a good chance that there's going to be an accident here because of the way the cars are behaving. The P4 is next to the P1 and they don't like each other. Whatever it's saying, okay, that's happening now on the track. And in fact, in real life, an accident happened on track on lap 27, and the flag was thrown on lap 28 in real life. This at the St. Petersburg's race earlier this year. And you can see we were able to predict that it stays up in probability for a little while because after an accident, there's a chance that when the cars come back to a restart that there'll still be another accident. So it stays up for a while, then you'll see it drop down. Now we're using truly generative models here to also, in this case, for lap time prediction, predict what all 30 cars will be doing in their next lap time around the track. And for this, we're using 2 different models per car times 30 cars. So we have 60 models running simultaneously on those A100s at the track with the streaming data coming in, updating these things as we go. And as you can see, we are in exactly the recorded lap times and the predicted lap times are in exactly the same distribution all the way through the race till the very end where it gets kind of skiddy and people are out of the race and this kind of a thing. But for the majority of the race, we can accurately predict what all 30 of those cars are going to do in their lap times, which means we can predict when we need to put our car into a gap, which helps us significantly on the track. And we can also, using the generative model, if you can deepfake a cat or deepfake a human that doesn't exist, or you can deepfake very accurately a novel with ChatGPT, you can also deepfake other things. So what we've been able to do is take all the other data that we have from 20 years of historical data and create a virtual sensor that is deep faking what the slip angle of the tire is. Now, why is that an issue? Well, we can't put accelerometers on well, you technically could, but you're not allowed to put accelerometers on the outside of the wheels of an open wheel racing car. Could be a bad day at the race, right? If you rub the tires, very expensive. But GPS is too slow. Video doesn't work very accurately. What are you going to do? Because the slip angle of the tires, where it's actually sliding, is not the direction of the tires. We have sensors for that. But where it's slipping is really kind of important to figure out where the tire is degrading and when it's degrading. And we don't have a sensor for that. But what we can do is correlate our lab data and other data from the other sensors, like the tire direction and this and that, to tell us and say deepfake what the 26 car is going to do with Colton Herter driving around this Alabama track, just like we can deepfake a nice picture of a cat that doesn't exist. And that's what you see here on this on the screen. Is the yellow is our predicted slip angle around that track. And if you can see a little bit of the green peeking up there, that's the actual data. That's the actual car driving around. So just like we get a realistic human with generative modeling, we can get a realistic virtual sensor that we don't have an actual sensor for. And this can be really helpful for driving our physical models and other things. We can create now synthetic, now that we know what the slip angle is going to be, we can actually synthesize data to test different behaviors, different track temperatures, different things in the very good physical models that we have. So this physical modeling with the generative modeling together creates a whole new world of what we can do in design and strategizing and different things with time series data. We're running this stuff on a military grade thing because in that truck, which is where all the analytics happen, it's in these ad hoc tracks, like we're in Monterey this week, and then we'll be in Toronto next week, a couple weeks from now. And it has to run through the desert at 150 degrees. There's a damper factory in the back that shakes when they're testing the shocks. Not a very good environment for a card-based NVIDIA card that's going to fall out. So we actually have a military-grade server in there with two A100s that are running live real-time in a very hot environment, a very hostile environment that's not always connected. And that's really important for a lot of the things that we do in the sensor area, is that these edge things where there are weather events, there are other events that you can't really predict, and you need your sensors and you need your local stuff and you need your IoT stuff to keep working, have the analytics keep working at the edge. And that's something that we believe in and we're able to actually produce for the racing team, but also in other industries. We've used these same models to we can deepfake track times. We can also deepfake drugs to be used for cancer, and we've done that successfully. Where we've actually got a drug in testing that was deepfaked using the same kind of technology. We are able to deepfake scenarios for trading based on streaming market data that we're doing with one of the banks, as I mentioned. Same thing for manufacturing schedules, different scenarios that will work different ways. We can actually do this synthetically now based on the distributions of historical data. And we can do, as I alluded to, we can put these virtual sensors and sensors, generative models that do this anomaly type of detection and predictive stuff. If you can predict a yellow flag, you can also predict when a network node is experiencing jitter that says it might go out. So think of putting like a little Raspberry Pi or a little microprocessor with this virtual sensor sitting there on each hop of a network. So that when you get your network, oh, these 100 devices are down, you don't just get that. You get, before that happens, this thing's jittering, then that one's jittering, then that one's jittering. Oh, wow, now we can roll the trucks here first and not everywhere. Same thing for network power grid management and a bunch of other different things that are distributed types of systems where we have distributed sensors and we need distributed intelligence. Thank you. If we have time to take questions or. When the yellow went up, so the question is the percentage of difference there, it did go up over 50%. So over half of a chance that you're going to see a yellow flag. And we had actually 4 occurrences of that. I wasn't able to show the whole video of that during the race. No false positives. There were actually 4 yellow flags. So it's pretty predictive. Now, are we yet at a point where we're going to just believe it and go? No, but it's kind of like the shift in baseball. It became illegal because it worked, right? And it does work. Yeah. Yeah. Yeah, so we're not using this for prediction in this case. With racing, there are going to be accidents, right? It's not about trying to prevent the accidents. You really can't do that, but there's a high chance because of the way the cars are converging or they're coming off of pit or someone has degraded their tires really fast, which means that they don't have as much tires as they think they do, and we can actually detect those kind of signals. They're in there. That's useful to know that, okay, there may be a yellow flag, so I want to pit my car first before they close the pits. Right. So here it's used for winning or losing. The question is, could that be used for predicting things in traffic? Absolutely. So if we had sensors on all these autonomous vehicles or even non-autonomous vehicles in a highway center, there are things, if we follow that over time, that we could say, you know, there's a high predictive flag right now, a yellow flag for 101 South today, just because of the way people are behaving coming out of the airport traffic at SFO, whatever it is, right? So yes, this could be used in that way. In traffic management, in emergency management, we're talking now to people who operate stadiums and they want egress for emergency if there's a cardiac event on the floor, Rolling Stones concert, a lot of older people there, and someone has a heart attack, we want to be prepared for that, right? And so predicting those things forward when they might happen, and also scenarioizing, generating the egress for when that does happen, how we should respond to that, simulating that way, can be really, in a lot of different instances, effective to prevent harm. We are, yes, the question is what kind of models do we use? We use all of the above is the real answer. These are ensembles of models. We'll use things as complicated as a transformer model when necessary, but they're very data intensive. We'll use GANs, which are kind of an intermediate form. Some of those using tensors, some not, depending on what kinds of properties we're trying to do. And we have on our Orchestra platform, we're able to benchmark these against each other. Some of the components may be as simple as a PCA. Principal component analysis thing where it just triggers on something. But we can use these in ensembles that work together, that this is looking at one thing, this is looking at one thing, and this is looking at one thing. And you don't need a nuclear bomb to kill a fly all the time. But sometimes you do need the high power stuff. So we'll use a number of different technologies applied to a problem, applied to a solution. All right, thank you very much. Appreciate it.